In this video, we're going to tackle question number 3 of the 2018 AP Chemistry FRQ. We're going to solve A, B, and C on this slide. It's a comparison of two ions of iron, the 2+ and 3+ ions. They want us to write a ground state electron configuration for the ion. They also want to take a look at which ion would be larger using principles of atomic structure, and also talk about the interactions of the 3+ ion with water molecules, why those are greater than the 2+. So I have gone ahead and pulled out this from the periodic table. It's a transition metal, so everything in this group is going to end in D6. So if I were to just do the ground state configuration for my neutral atom, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d6. Since I am looking at the Fe 2+ ion, I'm losing 2 electrons. I would start with 26, and let's just double check. 2 + 2 is 4, + 6 is 10, + 2 is 12, 18, 26, okay? And I'm going to lose them from the highest energy level, which would be this 4th energy level. So I'm going to get rid of those. So the electron configuration for the ion would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So that solves A for us. In B, they're giving us this evidence in the table above. That's our evidence. We're going to have to use principles of atomic structure to explain why the radius, so there's my claim, this is larger than this. Okay, so for B, the evidence they give me is that the 2+ is greater than that. And what I know is when I'm talking about atomic structure, you've got the same number of protons. So you have the same number of positive, negative, attractive forces. But your Fe 2+ ion is going to have more electrons than your Fe 3+ ion. Okay, so if you have more electrons, you've got more electron repulsion. And if you've got more electron repulsion, that's going to make that ion size greater than the Fe 3+. Okay, atomic structure, you're going to have to talk about your electrons or your protons or both of them. So make sure you're using what they ask you to explain why this phenomenon is happening. In C, same thing. They're saying we're going to use that claim, evidence, and reasoning. They're giving us our claim. Those ions interact more strongly with water molecules than the Fe 2+. And they just want one reason for this stronger indication using Coulomb's law. So if I take a look at Coulomb's law, the force of attraction is going to be directly related to the product of my charges, and or indirectly related to the square of my radius. So you could use two things. You could say, since the 3+ is greater than 2+, and the charges, the product of the charges is going to give you a greater force of attraction, you could use that. Or since it's inversely related to the radius, you could say that the Fe 3+ is smaller than the Fe 2+. So your radius is going to be smaller, which means it brings it closer into contact with the water, so that would allow it to be more strongly attracted. So you could use one of those two as an explanation. This part of the problem, a student has a solution with an unknown concentration of the 2+ iron ion, and they want to determine the concentration by titrating a sample of permanganate, which converts it from the 2+ to the 3+ ion following the reaction below. 3 parts to this section of the problem. They want you to write a balanced equation for the half reaction for the oxidation. Then they want you to calculate the concentration of the iron 2+ in the solution if it takes 17.48 milliliters of the potassium permanganate to reach the equivalence point. And then the last one is an equipment problem asking you why a volumetric flask would be a poor choice. So we're going to go through each part separately. In D, the balanced equation for the half reaction of the oxidation. So remember your oil rig, oxidation. So if I'm talking about my oxidation, that is the loss of electrons. Okay, and I'm going from my Fe2+ aqueous to my Fe3+. So there's the first part. Since I'm not gaining electrons, my electrons are going to be on this side. And since I'm going from a 2+ to a 3+, I'm only losing 1 electron. So that would be your balanced half reaction for the oxidation. So part E of this problem is a titration. And they want to know the concentration of my 2+ iron ion when I reach the equivalence point and that much of my titrant has been added. Remember, potassium is a group 1, so that's where this is coming. And the molar relationship between my ion and the permanganate ion is a 5:1. So I'm going to start with how much of I've got to figure out how many moles of my titrant was used. That's milliliters, so I'm going to need to convert that to liters. So I've got 0.01748 liters. I'm going to multiply that by the molarity, which is 0.0350. And that's going to give me my moles of potassium permanganate that was used. So that gives me 0.000612 moles of that solution used in that solution. You'll get 1 point just for figuring out the moles. Okay. Now I've got to use my balanced equation and that molar relationship to figure out how many moles of my ion were titrated. So I'm going to start with the moles, my titrant, 612 moles of potassium permanganate. From my balanced equation, I know I need for every 1 mole of that, I am going to consume 5 moles of my, iron 2+ ion. Okay, and when I do that math, I get 0.003059 moles of my Fe2+ ion. Going back here, the sample is in 10 milliliters. So to figure out the concentration, I'm going to divide that by liters, which would be 0.01 liters. And that will give me a final concentration of 0.3. We're going to keep it to 3 significant figures, 306 molarity. Part F of this problem, they've given you a choice of different glassware, and they want you to explain why the volumetric flask would be a poor choice. Don't get caught up in going over everything else. All they want you to do is explain why that one is a poor choice. So if you remember what a volumetric flask looks like, it's got this round bottom, and it usually just has one increment on it, depending on the size of this. Since this is 25 milliliters, that is going to make it accurate to 25 milliliters. But we're asked to use a 10 milliliter sample of the solution. So to measure it out in this is only accurate to 25 milliliters. So if I need 10 milliliters, this would be a poor choice. You don't need to get into an explanation of any of the other pieces of glassware for this problem. This last part of question 3 involves a separate experiment where the student's given some powdered iron solid that contains an impurity. They use a procedure to oxidize iron to iron 3 oxide, and they collect the following data from the experiment. 3 parts to this problem. We're going to break them up. The first part is we got to calculate the number of moles of iron produced, calculate mass percent, and then explain what would happen if there was some experimental error. So let's take a look at letter J. All right, so in letter J, we are given a mass of the iron with the impurity, and we're also giving how much of the iron 3 oxide is produced. So I'm going to start with how much of the iron 3 oxide was produced. And that is 7.531 grams of my iron. 3 oxide. Okay. I'm going to divide that by my molar mass. Molar mass of that compound is 159.70 grams. To figure out how many moles of my product were produced. Okay. And if I look at that formula, in that formula, if I look at the formula units for that, I'm going to have 2 moles of iron for every 1 mole of the iron 3 oxide produced. So that will tell me how many moles of iron were produced. And if I do all that math, I should get 0.09431. We've got 4 sig figs, so we're going to end in 4 sigs moles of iron. Okay. And we're going to need this piece of information for the next part of the problem. In the next part of the problem, they're asking you to calculate the mass of iron, the mass percent of iron in the original sample. So to do the mass percent, I'm going to take the grams of iron produced and compare it to the mass of the iron with the impurity. Okay, and multiply it by 100%. So I already know the moles of iron that were produced, so I'm going to use that information, and that we figured out in the last slide was 0.09431 moles of iron, and I'm going to multiply that by my molar mass. I know that in 1 mole of iron, my molar mass is 55.85 grams. So the mass of iron produced would be 5.267 grams. Okay, so 5.267 grams of iron is produced. I'm going to compare that to, this number, 6.724, and multiply it by 100%. And for that, you should get 78.33%. The last part of this problem, they say if the oxidation of the original sample was incomplete. So that I have, so at the end I've got not just what I'm expecting, but I also have my incomplete oxidation. So I've got both of these present. They want to know, would the calculated mass percent of iron be higher, lower, or the same? And they want us to justify our answer. So remember, our mass percent would be the mass of your iron compared to the iron with the impurity. Okay, and the way I figured out this was that I started with this produced and I divided it by the molar mass of that. Well, if I've got some of this present and I divide it by the molar mass of iron 3 oxide instead of the combination of the two, the mass of my iron is going to be lower than what I would think it would be. And if the mass of the iron is lower, then my percent mass is also going to be lower. And that takes us to the end of problem 3.